Hello, everybody. You might have heard some news from AWS recently about IPv6 and the IPv4 changes that are coming to the Elastic IP address space. I thought it would be useful to meet with one of our networking gurus, Pete Bird, and go over all of the changes that are happening. But to do that, I thought it would be better first to walk through what the heck is IPv4, what the heck is IPv6, what are the differences. But without further ado, Pete, the networking guru Bird, could you please introduce yourself?
Certainly. Hi, everybody. I'm Pete Bird. I am an engineering manager here at Caylent. My background is in networking, something I've enjoyed for a long time and continue to be interested in today. So I'm excited to dive into this with you, Randall.
Amazing. Okay, so I might get some of these dates wrong because I don't really remember, but IPv4 it was an evolution of a standard that was a combined protocol of IPv or Internet Protocol and TCP. They used to be one standard. I think it was called TCP3, and that was back in like the 80s. But IPv4 basically became its own protocol, separate from TCP, and it's a relatively complex protocol in and of itself. But there's a lot of different remedial protocols that got brought up over the years because basically as early as the late 80s, we knew we were going to run out of IP addresses. It was the growth of things like PDAs, if anyone remembers Palm Pilots and things like that, the growth of additional personal computers going everywhere. And it just became pretty obvious that, we were going to run out of IP addresses. And so people started working on IPv6. And IPv6, it's important to say, it's not just a extension of IPv4. It's not just you're getting longer addresses. It is actually a very different protocol. And there are different sort of things that happen. And, we could talk through all of the different, layers of the OSI model. If you're familiar with that, it's, you've got your application protocol at the top, and then you've got your networking protocols and all the other things through. But I thought the easiest way to talk through this would be to talk about a tale of two networks. So the journey of a packet in IPv4 versus the journey of a packet in IPv6, and all the different protocols that go around all of that. And we might skip over some things just because we have limited time, but I think this will help really understand what's happening with this change and why AWS is making this change. But before we do that, we have to understand something called CIDR, which is classless interdomain routing. So when we talk about addresses today, if you hear us using numbers like 192.168.0.0/8 or /32 if we're doing a single address, that's called classless interdomain routing notation, CIDR notation. And it's a common way of referring to IP addresses. And we'll put a little graphic up here that'll show you, CIDR notation for IPv4s versus CIDR notation for IPv6. And in IPv6, you get some letters. It's hexadecimal. It's much larger. But we'll also cover the structure of the packets as well. So I want to show you briefly the difference between these two, what we'll call headers or encapsulation frameworks for IPv4 and IPv6. This is actually a very helpful graphic. It's from Juniper Networks. Juniper makes some really cool kinds of capabilities and networking appliances and some great software too. But over here on the left, you see the IPv4 header, and you see it's got things like a version, a header length, a type of service, the packet length, different flags, fragmentation controls, a checksum, the source address, the destination address, different options, and then you actually have the data after that. So that's a whole bunch of information and kind of controls that you put into the header. Now, in the IPv6 header, you'll notice it's quite a bit simpler. We simply have the version, the traffic class, a flow label, a payload length, a next header, a hop limit, and then we have the source address and the destination address. It ends up that the IPv6 protocol puts a lot more work on the originating client of the connection to basically figure out how the heck it's supposed to route things along the way.
I just wanted to chime in and say one of the key differences there between an IPv4 header and an IPv6 header is that you have a variable length of an IPv4 header. I believe it's somewhere between 20 and 60 bytes, depending on the options that are included there, whereas the IPv6 header is a fixed 40 bytes in length, which really just paints a picture. It shows how much more efficient an IPv6 packet really is. It's a much more efficient protocol based on the way it's designed.
So what happens when we go to google.com on our web browser? What's really going on there? Well, at first you press enter, it fires off some kernel interrupt or something, and it goes and says, okay, cool, got this keyboard key. I'm going to go and take the google.com domain. I'm going to wrap it in IP and UDP and make a request from an ephemeral high port to DNS to give me the IP address of google.com. Whatever happens on Google's side, we're going to ignore for the purposes of this. We're going to get back our, and there's a lot of things that happen in between there with ARP and BGP, but we're going to skip over all of that just for the interest of kind of talking through things without getting too complex here. But from there, we get the address, and then we can start sending information. And that all happens in TCP, which, again, we're going to ignore the complexity of the SYN, the ACK, the whole dance there, just because we're talking about this IP layer. So one of the things that's happening here is we've got to get, on our LAN, we have to know how we're going to send the packet. So we've got to get a MAC address on our, which involves things like ARP. There's a lot of different security vulnerabilities there, and there's a lot of different network hardware that goes into mitigation techniques for that. And then we've got to figure out how the heck to route things over the internet. And I think this would be a great time for Pete to chime in. So Pete, what do you think about all of the routing in the IPv4 space?
Right. So basically we have the concept of routing protocols. So all the network devices between when a packet leaves a device, such as your laptop, and when a packet arrives at its destination, it's going to pass through any number of network appliances. First on your local network, it would be switches. Then you would get to your first hop router or your IP layer gateway or your layer 3 gateway. So these all speak different routing protocols. They can be manually configured routing protocols, static routing, in other words, or they can be dynamic routing protocols. So the internet itself speaks on BGP, Border Gateway Protocol, which is considered an exterior gateway protocol. And exterior means it's designed to operate outside the bounds of or between various autonomously managed systems or autonomous systems. You can think of an organization or a carrier network as an ASN or a collection of ASNs. Whereas once you get inside an organization, you have the concept of IGPs or interior gateway protocols, and OSPF is a perfect example of that. So basically, it's all these different routing protocols working in conjunction with one another and passing off to other routing protocols at various steps along the way in order to get a packet from its source to a destination.
If a packet hits a pocket on a socket on a port and the bus is interrupted as a very last resort and the address of the memory makes your floppy disk abort, then the socket packet pocket has an error to report. It's an old what if Dr. Seuss wrote technical manuals joke there. But, it does sound like it's really complex. And I think what's important for people to understand is like these things did not arise, in one design meeting of the IETF or in one RFC. Many of these things are remedial and are proposed over time, particularly the concept of NAT or network address translation. Could you talk us through that, Pete?
Sure. So NAT really arose out of the concern of running out of IP addresses. Basically, it takes a block of IPs that are considered non-routable on the public internet. You may hear the phrase private IP addressing thrown around a lot. That essentially means IP addresses that internet-facing routers just will not speak between them. They will not exchange these private address spaces. So NAT, network address translation, happens at a perimeter of a network typically where a routing device or a NAT device of some kind will take a source packet that is coming from one of those non-routable IP addresses and will translate it to a address that is publicly routable on the public internet. Over time, NAT also turned into a security measure as well, because it actually has that inherent benefit of masking the true source of a client.
And there's first of all, that requires stateful compute, right? Like there's got to be something, some appliance or some software sitting somewhere that's, taking, hey, this external address is currently talking to these internal addresses and knows how to route them. So that's one component of it that's kind of expensive.
Absolutely. Yes. And that also assumes that it's going to be a synchronous network path between your client and your destination. If you get into a situation where you have asymmetric routing, which very much of the public internet operates on asymmetric routing paths between the forward path of a packet and the TCP response back in the other direction, if you put a firewall in between that's performing NAT or any kind of stateful inspection for that matter, that can break connections.
Let's talk a little bit more about the security side of things. So there's a lot of different, networking appliances that evolved over the years as these networks became more complicated and as more routing protocols were added and as the complexity of what we were sending over the network evolved. Can you talk us through some of the different controls and security components of IPv4 in particular?
Certainly. The first one that comes to mind is IPsec. Essentially, that's encrypting your traffic in transit from its source to its destination. Oftentimes, this is done with some sort of a network appliance in between us, like a firewall that can terminate IPsec. Essentially, you're setting up a virtual private network or VPN. That way, your sensitive information is protected on its way over the public internet, for example. There are some cases where the clients and the destination can support that protocol as well and can handle that. We actually see that more in IPv6 than before. But so there's also the concept of IPVPNs. You may hear the term of MPLS being thrown around. Essentially, that is, as a customer of a MPLS WAN provider, for example, your traffic is typically isolated to its own IPVPN within that carrier's MPLS network. So that means your packets are tagged specifically for your traffic and not for anyone else's. And that also secures your traffic.
Gotcha. So we've got this whole sort of network that we've made our request to Google. We did a UDP request, which is kind of like, fire and forget. There's no sort of connection state maintained. We made a TCP request on, port 443 and did some SSL magic to get an encrypted connection over TCP. And then maybe if we're talking to some internal resource, we're going to go and have some IPsec tunnel that's going. And I remember setting those up a long time ago, and I'm very glad that I don't have to deal with that anymore. But we've kind of talked through the IPv4 side of things. I think we've covered, at a very high level, some of the complexity. I think IPsec on its own could be like a 1 hour long deep dive into all the complexities there. I guess one last thing to sort of talk about is the concept of a maximum transmission unit and fragmentation and its role in IPv4 versus in IPv6. So in IPv4, the fragmentation becomes the responsibility of many of the downstream routers along the way or networking appliances along the way. So with that, I think we've covered a lot of IPv4, and now I want to talk about the journey of a packet in an IPv6 network. So first of all, there aren't a ton of purely IPv6 networks out there yet. It's amusing because, even on my cell phone, I'll get over 5G, I'll get an IPv6 address, but then immediately when I do sort of a DNS lookup on, certain websites, I'll still get back an IPv4 address. So IPv6, despite being around since 1998, is still not as prevalent as one would hope. It's certainly more prevalent than it was, but the growth is relatively slow. So in an IPv6 network, the path is actually quite a bit simpler than it is in an IPv4 network. First, we There is still DHCP, but it typically uses things like, and there's still ICMP and all of these other sort of protocols, but IPv6 uses something called SLAAC, SLAAC, to kind of get its address and figure out what it's going to be sending as. And it can also use something called NDP, Neighbor Discovery Protocol, to find the link local addresses, essentially, or not necessarily link local, to find the hardware addresses. And an IPv6 address is 128 bits. It's 8 groups of 16 bits, and it has 3 scopes. It's got global, unique local, and link local. And so the CIDR notation for these are, ::1/128 is going to be your loopback address where you repeat stuff. ::/128 is unspecified. 2000::/3 is a global unicast. FC00::/7 is unique local LAN, so you can use this to build your whole local network. I can't remember exactly how many addresses that is, but I think that LAN has like 4 billion addresses or something like that, maybe more. And maybe that's an important point, is like the IP address exhaustion that we're experiencing is because we only have 4.3 billion unique IP addresses in the version 4 protocol. So to have that for the global internet, and then to have more than that on your LAN with IPv6 is pretty impressive. I've heard stats like you could give every grain of sand in the universe an address, or every grain of sand on the planet Earth an address in IPv6. And I can't remember the total number of addresses available, but maybe we could come back and say how many it is.
It's basically approximately 340 undecillion. It's a word that you don't hear very often. It's basically 2 to the 128th power IP addresses available within the IPv6 space, which is just astronomical.
Undecillion. That's a very crazy number. Do you know how many are in the link local address space?
Not off the top of my head. I would have to look that up, but
I guess
it
would
lot.
be 2 to the 128, and then 2 exponent 128 minus 7, so 2 to the 121, I guess, would be the total number. So that's way more than IPv4. Wow.
Yeah, absolutely. Just that alone far surpasses what we have available in v4.
That's incredible. I hadn't thought about that before. So a fun story is I actually failed the AWS networking certification, the professional cert or specialty cert, the first time I took it, because I took it way back in 2016 or something. It was a long time ago. And back then they didn't allow you to have a calculator. And the only reason I failed is that these questions took so long, and doing all the bit math or doing all the subnet masking math was killing me. I was like, wait, what's 2 to the 26 again? Okay, it took forever. And so they ended up redoing the exam, so you have to do a lot less of that math, or if you are doing the math, it's with a lot of whole numbers instead of the craziness that they used to have on there. And I think they give you a calculator now too, which makes it a lot easier. But anyway, fun anecdote. Okay, so we've got this, massive address space for link local and for unique local, and the header is much simpler. And our first hop, we do, instead of ARP, we use NDP, and then we do some router advertisements and router solicitations, and we configure these IP addresses. We use SLAAC, SLAAC, to do the auto config of the kind of routing and the IP address assignment. And this actually reduces local network bandwidth, because if you think about it, the client is just going off and saying, hey, I'm a device, here's my address, I want to do some stuff. Can you tell me the other things? The other clients can use NDP, and they discover their neighbors and their routers and things. And that reduces the overall amount of traffic on the network, because it's not having to go and say, oh, ARP, or oh, this, or oh, DHCP, let me sit here and try 15 different addresses and see if I get one that works. It's just like, there is even built into the protocol something called DAD, which is duplicate address detection. But like the chances of it happening are much lower, even on congested and large networks. Um, so then, there's some enhanced routing protocols that go on here. And we have like route aggregation, so we can have hierarchical routes. So if you think about IPv4 routing, because of all the layers of NAT, it can be really complicated, and there's like a lot of information and compute that goes into getting a packet to the right place. Whereas in IPv6, it can be a little more hierarchical. So a router only needs to know I need to go to here, and then the next router in the line figures out what's next. And you can have much larger sort of blocks and fewer random rules that are spread out across swaths of IP addresses that are not contiguous. So just the general amount of compute and work that it takes to route an IPv6 network is less, and it takes less traffic. And yeah, I mean, the global IPv6 is great. It would be amazing if we all moved to it. But then we get into the real world. And before we jump into that, I wanted to give Pete a chance to kind of hop in and chat through some of your opinions on IPv6 and some of the security components of it. And then we'll talk about the real world side of things.
Yeah, just to kind of go back to your point about IPv6 routing structure and kind of the layers in between. It's really just a result of the maturity of the endpoints that exist. Really puts the onus on some of these other functions that were performed by IPv4 on these endpoints instead of on the routing protocol itself. And it really allows IPv6 to be a true routing protocol and just do that and do it well. So when you talk about all the routing devices in between, they aggregate IPv6 a lot more efficiently than they would IPv4, and thus the routing tables are essentially smaller along the path, and it just makes routing that much more efficient.
Awesome. Well, I know that you have worked with a number of our customers on the transition to IPv6, and we can talk about the protocol differences all day, but I think what really matters to people is what is it like in the real world when you actually go and do this work. I was wondering if you kind of talk through your experience there.
Yeah, you really kind of touched on it. There are very few pure IPv6 networks out there. Most everything that we've seen, and as we help our customers transition, it's going to be what we call dual stacked, meaning your IPv4 environment is going to continue to exist as it does today, and we simply enable your infrastructure to speak IPv6, meaning we configure IPv6 on routers within your AWS cloud environment. We enable IPv6 within your VPC structure. And then we have to consider things like what AWS services support IPv6. And AWS has a great page published that documents this. And when you go to that, you'll see that most everything that's most of the services that you would need to consider for this support IPv6, at least in the dual stack sense. And outside of that, there are lots of other considerations that people perhaps don't think of, such as the secondary and tertiary services that your core services rely on. One example that comes to mind are log consumers or log parsers. Like all these things have to be able to speak IPv6, and many of them perhaps don't today. Another thing is your application logic. Is your application designed to be able to speak IPv6? So really, it is a truly full stack analysis and transition just to get from one to the other. But again, the most common scenario we see is that it will be operating in parallel IPv4 and IPv6.
And how much longer, if you had to guess, do you think will be in parallel? I know I'm putting you on the spot there.
Yeah, that's a question, isn't it? Probably it's going to be a years long effort. I'll say that in most environments. To be quite frank, I don't know if there's an end to IPv4 in sight, partially because it's been in operation for so long and it just works, and the world is very familiar with it already. So there is a huge learning aspect to IPv6 and getting used to just reading and being able to interpret an IPv6 address. IPv4 is very much binary and binary math. It's kind of easy on the eyes for those of us that are in working with networking, whereas IPv6 has hexadecimal. Now it's not just binary anymore. Now you have A through F. You have letters involved, and like all of a sudden there's letters in my IP address. So it takes a lot of getting used to.
And I think, there's probably implications on a macro level for some of these companies as things move to IPv6, like Cisco or, F5 or even Juniper. Maybe it's to their advantage that IPv4 sticks around because they can sell some of their routers for longer. Because as IPv6 gets adopted, you don't need as many of these devices. You don't need as many of these appliances on the path. That said, I do think many of these networking folks have been good stewards of the internet and kind of building the right appliances. I have a fun stat for you. So as of May 12th, 2024, only 44.33% of Google's global internet users are connecting over IPv6. So we're not even at 50% yet. And if you look at the per country adoption, there's pretty solid adoption in the US, still below 50%. The country that has the highest adoption rate is actually France at 75%. And this results in a pretty significant latency improvement for them. And then, if you look at, Africa and the Middle East, there's really very little IPv6 adoption, with the exception of Saudi Arabia, which is at 62%. So I mean, it's pretty interesting to see these sorts of stats. I wonder if there's any particular legislation or something in France and Germany that leads to them being at 70%. Do you think, here's kind of a macro question for you. Do you think as the internet proliferates to the rest of Africa that it's more likely they'll just go straight to IPv6, or do you think they'll have to have an IPv4 network in addition to that?
I think it's, as with anything, a lot of it is going to be driven by requirement, right? So if you take a step back and look at what out there on the internet was first or an early adopter of IPv6, it comes down to mobile devices and IoT devices, things where there could be potentially millions of them connected to any single network. So I think the answer to that is really going to be driven by what are people doing, what are they using, what are the business drivers, the local economies in those various countries, things like that. So I think potentially we could see a much more steeper hockey stick adoption rate in countries and parts of the world where there isn't already massive IPv4 adoption like there is in the rest of the world. So it'll be interesting to see the directions things go. That's for sure.
Yeah, I think it's cool because if you think about the evolution of cellular networks, Africa kind of leapfrogged a lot of other countries as they were moving into, you can get 5G in many places there because they bought routers that, made sense to them at the time. And it was a later technology and there was nothing really to migrate or replace. So I wonder if the same thing will happen with IPv6 as more of the internet connectivity rolls out there. Anyway, moving back to sort of the enterprise costs of moving to IPv6, one of the changes that happened recently is that AWS began charging for allocated IPv4 addresses. So they used to only charge for unallocated IPv4 addresses, which was a good thing to do because it incentivized freeing up addresses and stop people from just sitting on them. and helped reduce some of the IPv4 exhaustion. But now, because we are, totally exhausted of IPv4 addresses, AWS has begun to charge for the IPv4 addresses even when they are in use, which could come as a shock when people review their Q1 bill and they're like, "Oh, what is this extra charge for me?" Could you, Pete, talk to some of the transition costs that are associated with moving to IPv6 and reducing that spend of the IPv4 addresses?
Oh, absolutely. So moving to IPv6 on your public-facing AWS environment, once you're migrated, there's no charge. So, I mean, that's an obvious, huge benefit. I believe the charge for all your allocated IPv4 elastic IPs or EIPs is like half a cent per hour per IP, if I'm not mistaken. So, I mean, it's quite obvious when you think about that. So, really, the biggest impact are going to be our AWS customers who have a very large public presence, a very large public-facing presence, where there's a requirement around static public IPs. So, yeah, I'd say that's a huge incentive right there.
And then can you talk about some of the gotchas that people run into, 6 to 4 and, some of the other sorts of things within the VPC that we have to keep in mind?
Yeah. So when you're going from your internal VPC environment to the public internet, the outbound direction, AWS offers the egress only gateway, which is, you can think of it as the IPv6 version of their managed NAT gateway, except the difference is there's no charge. So it's obviously another incentive. Beyond that, really, you just have to think about dual stacking your network, dual stacking your subnets, your VPC. You have to attach v6 CIDR to your VPC and just build upon it that way.
I also think it's important that customers test these networks because there's a lot of random hidden things that you may not be aware of. Let me tell you about one we found recently. So one of our customers was using Stunner, which works with WebRTC and Turn and other services, and they deployed this, and we had them in a dual stack network, and we could not figure out for the life of us why this thing wasn't working until we finally got into the code of Stunner, and it turns out it doesn't support IPv6 loopbacks. So we had to turn off. So we kept the dual stack network, but on the pods that we were deploying Stunner to, we had to turn off the IPv6 loopback because the networking layer that Stunner was using was helpfully supplying the loopback address, and Stunner was saying, "LOL, I'll try to bind to this," and then it had no idea what to do. So you run into all these random misconfigurations and things that haven't been updated or tested.
Yeah, so that's one of those scenarios where you have to, run TCP dumps and do packet captures to really get to the bottom of it because it's not inherently obvious. Yeah, that could get real fun.
One of the tools that I found really useful, it actually would not have solved that loopback problem, but the VPC reachability analyzer has been really helpful over the years. And, AWS has evolved their networking capabilities quite a bit. Cloud WAN and Transit Gateway now make it pretty easy to work with these things and even to visualize them. But overall, yeah, I think things have really kind of evolved a lot over the years, and I've been impressed with the rapid adoption of IPv6 within AWS, although there are still some services that don't support it. But will SimpleDB ever support it? I don't know.
Yeah, I agree. It's really good to see that AWS is keeping up with things with IPv6 in mind. So yeah, I would echo that. Seeing things like AWS Cloud WAN, Transit Gateway, it really makes it easy for customers as they think through how they would adopt IPv6. Well, they're just simply not blocked anymore by all the core networking services that AWS has to offer.
Yep. And, it's nice that we have NAT 6 to 4 and DNS 6 to 4 to help in the VPC side of things. But with that said, I want to take a turn here now that we've talked through the real world implementation. We've talked through the journey of a packet for IPv4, the journey of a packet for IPv6. Let's talk about some of the future, stuff that could happen within IPv6. So, we've got IoT, smart cities, one address for every grain of sand. What do you think is going to be unlocked with the future of IPv6?
Geez, I don't even know where to start there. I have to imagine that AI is going to come into this somehow. Um, I think
My
that's
link
inevitable.
space is all, agents that I've provisioned, and they're all having their own IPv6 address.
Yeah, I just see at a real high level on a very broad scope, just the simplification of communicating over the internet between end devices, one way or the other. I think IPv6 is really like IP networking in general. It's something that happens under the hood. Um, when it often goes unnoticed and unrecognized. It's one of those concepts that when it works great, you don't notice. And that is on purpose. People don't ever call and call up to say, hey, the network is working great today, right? You only hear when the network is broken and something doesn't work. At the same time, it is a construct that when it doesn't work, nothing that rides on top of it works at all. So it's very noticeable. So I think moving forward into IPv6, we'll see a lot more stability. We'll see a lot more reliability and resiliency just overall. So I think that's probably going to be the biggest realization of what IPv6 has to offer over time.
I love it. Well, one of the things that we found with our customers is that this transition is non-trivial. It's not as simple as flipping a switch. And so we developed a couple of offerings. One is our networking modernization assessment and solution. We'll provide a link for that in the description of this video, as well as our IPv4 versus IPv6 infographic. We'll show that as well. And I think, we kind of stand on this weird sort of cusp where IPv6 adoption is really starting to take off, and who knows really, because they've been saying that since 1998. But I think the economic pressure at this point is such that the need to move to IPv6 is stronger than it's been before, and we want to help our customers get there and be able to take advantage of some of the new capabilities that exist within those networks. So not just doing it because it's an economic thing, but also doing it to unlock new capabilities. So Pete, I want to say thanks again so much for taking the time to be here with us today. I know that you are crazy busy. Your customers are always asking you the really hard networking questions, and I sometimes ping you on Slack and ask you the really hard networking questions. So I just want to say thanks for taking the time to show up and have this conversation with us today.
It's been my pleasure. Thanks for having me.
And with that, I'll say thanks for listening, everybody. If you do need help with IPv6 modernization or any sort of networking modernization, please reach out to Caylent. We do this stuff all day, every day, and it's a lot of fun for us.